All right, to advanced calc, we're going to work on section 5.4 of the ice sheet. If you look, I put way too many problems on the ice sheet, but in class we went over question 3. We did pretty quickly and used a lot of facts to hit those hard. And question 5, I did in class. I cheated a little compared to the back, and I used the fact that we technically don't know yet that if you have a bounded derivative, then you're uniformly continuous. We're going to prove that in chapter 6. But I don't mind using that. If you want to use that on this homework, you can. Okay, so the next are 7, 8, 9, and 10, and I'm going to skip 15. So 7, 8, 9, and 10 are all about whether tweaking things a bit keeps you uniformly continuous. So we're going to have 2 proofs and then 2 just some counterexample stuff. So 7, I'm hoping you have the textbook in front of you. I'm not going to write these out. 7 says if you have a function from D to R, it's uniformly continuous on D, and then you have some real constant, and I want to take the function K times F and show that's uniformly continuous. So this is a classic trick where you have one limit or one continuity or one derivative and you're trying to show another. So because F is UC, you can say that given, so we're going to say let epsilon greater than 0 be given. And then because F is UC, then there already exists a delta such that x minus y less than delta implies f of x minus f of y is less than something. And we're going to fill that in a minute to be the thing we want. It's probably going to be some variant of epsilon. So if I had like epsilon over 2, that would be fine because f is uniformly continuous. So it works for any epsilon, even some variation of not the epsilon we're looking at, but some different one. Okay, well, our expression, if we want to use this delta in this situation, I just need to think about, that's not necessarily true. Sometimes use a different delta, but here I think it works fine. If you think about k f of x minus k f of y, well, and I want that less than epsilon is my goal. Well, if you pull the k out like that, then you would have the stuff above. Sorry, I'm running out of space here. Then this, going back to this spot, it should just be epsilon over epsilon value of k. That's a positive constant. If my stuff is less than that, everything will work. Okay, I got kind of cornered here at the bottom, but let me do this now from the beginning and try to write out somewhat carefully. All right. Let's go to the next page. Okay, to start from the beginning, we're going to say let epsilon greater than 0 be given, and then there exists delta such that x minus y less than delta implies that f of x minus f of y, because f is uniformly continuous, is less than, we're going to do epsilon over epsilon value k. K is already defined in the problem. And now we're trying to talk about kf, so let's use the same delta. So that's what we're going to be using. So then I want kf of x minus kf of y. That's my new function. Now I'm going to do a little bit of algebra. K out of the absolute value, but it stays in absolute value. I factored it out, basically. And now that stuff, I did this backwards. That stuff on the right becomes less than epsilon over epsilon value k, but I also had the one on the outside, and so that becomes epsilon. So there's a lot of words I should be writing in between, but that's the general way that's going to look when you're done. Okay, so that's number 7. Let's go ahead and go to number 8. Okay, so number 8 says you have f and g are real value functions that are uniformly continuous on a domain D, and the g of x is not equal to 0 for any x. And it says find an example that the quotient function still need not be uniformly continuous. So just think, for several of these counterexample problems, don't make it harder than it is. First, just think of a function that's not uniformly continuous. So if you think about, and we're thinking about division, so think about a fraction. This guy here we talked about in class has vertical asymptotes aren't going to work for this. So if you do this like on 0, 1, it looks like that. That's not uniformly continuous. So your functions then would be constants are uniformly continuous and so are lines. So those are the 2 functions, f and g. And then Part B says prove that it works if D is compact. Now for part B, since D is compact, I'm just going to use facts about continuity. So because F and G are both uniformly continuous, so F, G are uniformly continuous, that implies continuity. And then G is not 0, and so you already have a theorem about continuity that makes F over G continuous. And then you have continuous plus a compact interval, and then, or a compact set, I should say. And so that makes F over G uniformly continuous. So it's kind of that idea of a direct proof of having a situation and moving back a step and then coming back forward. So move back to the continuity situation. You know that works for quotients, and then you're in a compact interval. So you have uniform continuity. Now notice that's a difference, right? Quotients of continuous functions, as long as the bottom isn't 0, are continuous, regardless of the interval. Uniform continuity, that's the whole point of this problem, doesn't necessarily work unless you're talking about compact sets. All right, so that was the end of 8. So let's go ahead and go to 9. 9 is probably the toughest one here. It says prove or give a counterexample. It says you have a function from A to B that's uniformly continuous, and then G from B to C is also uniformly continuous. And I want to prove that G circle F, prove or disprove, from A to C is uniformly continuous. This is actually true. And so the way we're going to prove this is just kind of go strictly by definition here. So I'm going to need a lot of space. I'm going to erase that, but that's the problem statement. And our overall goal is we want to say that given epsilon greater than 0, I want to choose a delta, right? And then my final goal is to say that G of f of x minus G of f of y is less than epsilon. Well, G is already uniformly continuous, so you need to think of f of x and f of y as the inputs. So I need to find, so because, well, I should say I don't need to find, it already exists because G is uniformly continuous. This is true when there's a delta 1, so that think of these as x values, f of x minus f of y less than delta 1 here, because this is the x value. So there's some delta 1 where this is true. Now, you have to think about this 2 different ways. That's the input for G, so that's why I wrote delta, but it's also the output of f. F is uniformly continuous. So thinking back to that, this isn't really in the right order. For that delta 1, there exists a delta 2 such that if x minus y is less than delta 2, then you get this. Now this looks, so delta 2 is the guy you want. This looks correct, but it's not in the logical order. So that's kind of all the pieces. That's where it's coming from, but I should put this in the right order. So I'm going to write all this again. Now that I've got the idea of the proof, I'm going to do it logically from the ground up. So let's get rid of most of this. I guess all of it. So let's go back to, say, epsilon greater than 0, and then there exists, I'll try to use the same one as I did before. There exists delta 1 such that f of x minus f of y less than delta 1 implies G of f of x minus G of f of y is less than epsilon. Okay, so that's not the delta 1 I want to pick, though. I want x minus y. And normally we have the delta we want for the beginning, or for the whole thing right at the beginning. This one just kind of, it's a little bit out of order, just the way the proof works. Okay, then this is because that's, this is because G is UC. And then since F is UC, there exists delta 2 such that x minus y less than delta 2 makes f of x minus f of y as small as we want, including less than delta 1. So the point is, choose delta equal to delta 2 and the conclusion follows. So I don't have room for that. So what do we do? The square? That's the end of a proof, right? So you kind of work everything backwards, then you end up with the delta that you want at the end, and rather than at the beginning. You can't really say choose delta equals delta 2 at the beginning, because it's like, what the heck is delta 2? Well, it comes from that sequence of stuff. So that's why you actually kind of say it at the end for this proof. In any case, that's the end of that problem. And then the last problem is question 10. We're skipping 15. And this is another true or false problem. All four of these, I think, or 8, 9, 10 were all about showing something's true or false. And so 10 says find two real valued functions f and g that are uniformly continuous on a set, but their product is not. So I want f, g, u, c on D, but f, g, not u, c on D. Okay, so in general, when you're thinking about these problems, you should think about examples we did in class. I tried to give you the basic tools of functions to think about. And we did 1 over x, we did root x, we did x squared, we did lines. And we think about which of these looks like a product of two things. It was x squared. We showed that was not UC on R, but lines are. So this was not UC, but this was. So if you think of f and g both as x, those are UC on R, but fg equals x squared is not. And that's all you need for number 10. All right, so that is the end of the 5.4 ice sheet.